Okay, so let me remind you again, we are trying to find well-behaved tangle invariants by the Young-Baxter method, which requires that we found an E-Hop algebra, so an involutive Hopf algebra, along with an element in it called the R element, and denoted R. And these elements, this algebra, should satisfy lots of axioms, and I think this is a summary version. It's not, doesn't even include everything, but associativity, co-associativity, it should be unital, so it should have a unit and a co-unit. The product and the co-product should be appropriately compatible. S should be an involutive, meaning S squared should be equal to the identity, and this is actually a key requirement because later we will drop it. An anti-homomorphism, there should be this identity here, so delta followed either by S tensor 1 or by 1 tensor S followed by M should be the identity. R should be compatible with the coproduct and and the multiplication. So basically, if you double a strand on a crossing, you get two crossings multiplied together. So that's a compatibility of delta and M. And it should be compatible with the co-unit and with the antipode, and it should satisfy the Young-Baxter equation, which is really Ridermaster 3. That's quite a lot. It will stay a lot, but we will get used to it. Anyway, we were in the process of studying one such specific algebra, and my plan for today is to implement it. Partially to see how implementation works, partially to see what do you get something interesting, and we will learn something from it. So the algebra is, so given a finite group G, you let WG be the vector space generated by symbol W alpha beta, where alpha and beta are in the group. So the dimension of this vector space is the square of the order of the group. And you define all the operations by explicit formulas. And last time I've justified them, so I will not do it again. But basically, if you want to multiply W alpha beta with W gamma delta, there is an explicit formula. Basically, there is an explicit formula for everything. I want to implement all of this today, and then use it to actually compute the invariance, the resulting invariance of knots, and hopefully learn something from it. Okay, so I wrote, I hope these classes with the implementation will be bearable, because I will be trying to do computer stuff on the board, but the right way to do computer stuff is to play with your own computer. In fact, the right way to do mathematics is to play with it yourself also. So maybe it's not that different. And I remind you, you're more than welcome to get the student version of Mathematica, and I will cover it from my grant if you're consistently using it till the end of the semester. And then everything that I do, I post on the web, so you can play with it later. Okay, so I'll just do, so first of all, just for use later, I want to load a program that a package that I wrote a long time ago, and that defines lots of knots. So basically, with this package, if you write all knots with 3 to 5 crossings, it will tell you that there are 4 of them. And if you write PD, so I remind you the PD notation from before, and you apply it to this list of all knots, so this applies the function PD to every element of that list. So you will get a list of 4 PDs, one with 3 crossings, the second with 4 crossings, and 2 with 5 crossings, and that corresponds to the first 4 nodes. But I could have done, I could have gone to higher numbers. I didn't have to stop at 5. Anyway, the next thing is to define a group. Okay? So I am defining a function called declared group. Declare group. And declare group called with an argument s sub k is the following. So this leaves it open for me to define a different declare group package called declare group a sub k. And then I'd have the alternating. And then after writing it, I'll have the alternating groups. So this is a module, meaning it's a thing which is allowed to have local variables. And the local variables are alpha, beta, e, and the gammas. So anything that ends with s should be read as gammas, as opposed to a single gamma. And then, where are the gammas? I think it's a no, I do use it. Okay. The first thing we do is, so this is actually bad programming, because you should never have a program defining global variables, especially not when the global variables have single letter names, because what if somebody else wants to use the letter G for something else? But since this is a single-use thing, I'm allowing myself to do bad habits, to work with bad habits. So, first of all, I clear the value of G. G will be the group, N will be the order of the group, lowercase g will be a specific element, the elements of the group, IOTA will be the index of an element, so I'll have a bijection between the element and the natural numbers, and this will be the index of an element, which natural number it corresponds to. M will be multiplication, and inv, I will not tell you what it is, you can guess. Okay? Anyway, so first of all, I clear these so that I can redefine groups. So I define and then redefine, and then every time I redefine, I clear the old definitions. Then I let, okay, so K was the rank of the permutation group. So I look at range of K. So for example, suppose K is equal to 3, then the range of K will be the list from 1 to 3. And then permutations of the range of K. So I'm just using built-in things in Mathematica. It's kind of nice when you have all the basic mathematics already implemented, and you can then just write on top of this. So permutations of the range of K is, well, the 6 permutations, but they are written in, what is it called? When you write pi 1, pi 2, pi 3, the images of the elements. Is there a name for this notation for permutations?
Cycle notation.
No, this isn't cycle notation.
Cycle notation.
So this is funny because the Mathematica program that produces permutations just produces all the permutations. And in fact, it didn't have to, I didn't have to run it on 1, 2, 3, so I could have done this just as well. Permutations of any other list. So Jesse, Leonard, Jessica. Sorry. This is again J. Adrian. Okay? And you'll get all the permutations of these. Okay? But what I actually want is cycle notation, because the routines to compose permutations are written more clearly in cycle notation. So hence, the first thing I do is I compute the permutation cycles of all of these. So permutation cycles of all of the permutations. And okay, so the identity permutation has no cycles. The next permutation, so this is the permutation 1, 3, 2. So 2 and 3 are a cycle. So there is a single cycle, and it's the cycle which cycles 2 and 3, and then so on. Yeah?
Does permutation cycles assume an ordering on the elements?
I think it even assumes that there are 1, 2, 3. Though I'm not sure.
So you couldn't run this on the JLA example?
I actually don't know. That's a good question. I've never tried. So let's copy paste it and run it on the permutations of JLA. Yeah. It gives me error messages. It actually assumes that I'm permuting 1, 2, and 3. And 4, maybe. Okay? Anyway, then, so G is all of these. So once I set G to be this, you know what, let me copy paste all of this so that I don't have to scroll back and forth every time. So when I when I set G to be all of this, then G is just the list of elements of the groups. Then n is the length of G, so hopefully it will come out to be 6. And then for alpha, so this is the do loop. For alpha running from 1 to n, I am setting G sub alpha to be called E, which is also the group element number alpha. It's actually almost meaningless, this line. But the more interesting point is that I set the index of E to be alpha. So now for every element, I have the IOTA function, which tells me what is its index. So, you know, if you want to see the effect of it, let's ask Mathematica what are all the definitions associated with the symbol IOTA. And right now it's saying we don't know anything. But once I run this line, it will define IOTA for all the group elements, and for each one it will return its index. So now if I write what is IOTA, it will tell, so the index of the identity permutation is 1. The index of the cycle 2, 3 is 2. It's just some numbering of the elements of the group. The reason I'm doing all of this is because when I would want to do group operations with many group elements later on, I don't want to store each group element each time, because they're big, they're heavy, they take up memory. Instead, I want to say element number 4, and that takes up just 1 byte of information instead of or word of information rather than plenty. So anyway, now let's go back to the program and copy paste it once again so that we don't have to. So okay, the next thing is I defined a multiplication table. So this is kind of fine. I define the multiplication of an empty set of elements to be 1. Meaning the index of the identity permutation. So that's actually the identity element. Then, for every pair of elements alpha and beta, I define the product of alpha and beta. So alpha and beta are really integers. So I define the product of alpha and beta to be, you take the group element number alpha, the group element number beta, apply the permutation product to them, and find the index of the result. So really, I've converted this to a product of integers, right? Of integers from 1 to 6. Well, and I do this for all alpha from 1 to n, and for all beta from 1 to n. So let's see what's the effect. So here is this line. First of all, let's see what is m. Right now, it's nothing. And once I execute this line and check what is m, So the product of element number 1 with element number 1 is 1. The product of element number 4 with element number 4 is 5, and so on. I don't know, they come up in some random order. Then I define the unary product, so the product of a single element to be that element itself, just for completeness, and the product of alpha with beta with any further list of gammas to be, you first multiply alpha and beta and then multiply it with gammas. So now products of arbitrary length things are defined. And finally, I define the inverse of alpha for every alpha to be the index of the inverse permutation of G alpha. So now I have a full implementation of the group, and you can do calculations. So let me execute it, and now I can do calculations. I don't know if I should do it. I mean, so let's conjugate element number 2 by element number 3. So M, the product of the inverse of element number 3 with element number 2 with element number 3. So, oops. Done. Oh, sorry. I've run the program I've executed the line that defines the program that declares a group, but I didn't actually declare a group. So now I have to declare the group to be S3, and now the group is defined, right? So I wrote a program to declare groups. I didn't actually declare one. So now if I'll copy paste this, I will get, well, you know, actually, let's look what are the elements of G. So what we've just computed is that if you conjugate the 2-3 cycle by the 1-2 cycle, you get the 1-3 cycle, and I think it's right. It better be right. Okay? So just for fun, I'm redeclaring the group S3. Well, actually, I don't need to. It's been declared already. So here's the multiplication table. Okay? Good. That was the hard work. Now comes straightforward implementation of this. So first of all, I want to define, okay, no, there is something clever going on. So not only I want to define WG, I want to define the tensor product of an arbitrary collection of WGs. Oh, so I want to define WG tensor WG tensor WG. Okay? And my convention is that tensor factors are always labeled. They're not numbered from 1 to left. When I write them from 1 to left, it's just because I'm lazy. My convention is that they should be labeled. So say this one is labeled Jesse, this one is labeled Leonard, and this one was labeled Adrian. Okay? Then I need to tell you what are the elements of such a tensor product, or a basis for the elements of such a tensor product. So a basis for the elements will be WG, elements of the form W alpha beta with index J, W gamma delta with index L, W epsilon, what's after epsilon? Eta? Yeah, I don't know, eta, with index A. So what we label elements in a tensor product will be simply products of such W elements. Okay, this corresponds to what other people would write as W alpha beta tensor W beta delta tensor W epsilon eta. Okay? So now I want to produce the basis of of arbitrary tensor powers. So if you give me any set A, I want to produce the basis of WG to the power A. Okay? So if the set A is the empty set, there is only one element in the basis, and it's 1. If the set A, if the set A starts with the letter I, or the symbol I, and then there are some further i's, then I create a table of Wi alpha beta and multiply it by the basis, which just, so this will be a list. So multiplying a single element with a list will produce a list of all the products. So maybe the best is to show examples. So if I do the basis of the empty set, I get 1. If I do the basis of J for Jesse, one single tensor factor called Jesse, then I'll get Wj with all the possibilities. If I'll do the tensor factor of two bases of two factors labeled 1 and 2, so this should be 36 squared basis elements. And fortunately, so you know what, actually let's pipe it into the command short, which means skip almost everything. So basically, the elements are W111, W211, up to W166, W266, with 1294 missing elements in between. Okay? Good. Okay, now let's implement, and now everything is absolutely trivial. So, what's the product? So, if I want to multiply the thing in tensor factor I with the thing in tensor factor j, put the output in the tensor factor which I call k. So, right, multiplication goes from algebra squared to the algebra. So I have two input tensor factors and one output tensor factor. So I want to apply this multiplication element, this multiplication operator, to an expression E. What do I do? Well, I expand E. This is just the technicality. And then every place where I see, so I apply the rule which says, so this arrow means, so this slash means apply a rule, and this arrow means a rule. And the rule is, every place where you see a WAI alpha beta, a WJ gamma delta, you apply what is written here. So if the product of alpha and beta is equal to the product of beta and gamma, you output whatever is written here. So W of alpha and the product of beta and gamma. Otherwise, you output 0. That's what the Kronecker delta function does. Likewise, everything else. So eta I just multiply the input with the sum of Wi alpha 1. M of bracket is just 1 in the group. So this is this. Then, so let's execute it. Likewise, the coproduct. So if you want to apply the coproduct to the element sitting in tensor factor I and write the output in tensor factors j and k, all you do is you look for every place you see a Wi alpha beta, you replace it by the thing given by the formula. Basically, same for everything else. So let's execute all of these so that we'll have them. And then it's just a basic testing. Suppose I want to test associativity. I set the basis B to be the basis. So it's the basis where the tensor factors live in factors 1, 2, and 3. And then I multiply 1 and 2 into 1, and then 1 and 3 into 1. That's associating on the left. And I check if it's equal to multiplying 2 and 3 into 2, and then multiplying 1 and 2 into 1. That's associating on the right. Is this equal? The answer is yes. Check if eta is a unit. So take the basis, add a unit in tensor factor number 2, multiply 1 and 2 into 1. So basically, I've added a unit and then multiplied. It should be so this should be equal to the basis, what I started from. Likewise for the multiplication on the other side. And if I'm lucky, it should give true, and it does. So, you know, we could go through each of these. I don't know, it's probably boring, yes?
So each of these computations, like, it represents, or each of these lines represents one computation for every basis element.
Yes.
So it's,
Yes. So in fact, I mean, you know, so like let's do the associativity in a little bit more detail. So instead of, so let B be the basis, well, that's a huge, terrible thing with 46,651 things missing, not shown when I'm printing. But you know, each thing is of the form a W in factor 1, a W in factor 2, and a W in factor 3. So let's take a random choice out of this. So let the new B be a random choice within this basis. Okay? So that's just a single element. Now let's check if the associativity holds for this single element. So I'll multiply it as on the left. Oh, it came out 0. Better come out 0 on the right as well. So I copy paste and multiply on the right. Well, it also came out 0. So in fact, many things come out 0 because there is a Kronecker delta in the definition. But not everything is 0. So you know, if you think everything is 0, let's rerun again. What is the basis? So this is again the basis. And then let's compute the left-hand side for all elements of the basis. And if it's a long list of zeros, we lose, but it's not a long list of zeros. Okay. Okay, likewise, I can check that eta is a unit, it works. I can check that basis, the coproduct is co-associative, that the epsilon is a co-unit, that epsilon is a morphism of algebras, that M is a morphism of algebras. Basically, go through the list. Each of them is essentially typesetting a mathematical equation in Mathematica, in the program Mathematica. That's all. You know, maybe I'll just rerun this whole chapter. Why is it taking time? I don't know. But anyway, everything prints true, so we're done. Oh, except for Ridermaster 1. So does Ridermaster 1 hold? So what is Ridermaster 1? So Ridermaster 1 is right, it's this. So this is an R. So really it's R in positions 1 and 2. And then you multiply 1 with 2. So, right, so you connect this end to this tail, so this is multiplying 1 and 2. So, I take R1, 2 and multiply 1 and 2, putting the output in 1. This is one computation. And the second computation is just the identity on 1. And they're not the same. They're nearly the same. Well, they're Well, if you look carefully, this is a 2, this is a 1, this is a 3, they're not the same. So, so we actually have an invariant of framed knots, which is not surprising, okay? By the way, it totally makes sense, right? If you remember the topological interpretation, then we were counting representations into the group in which alpha, W alpha beta counts representations in which the meridian is alpha and the longitude is beta. So in the identity element, the meridian could be anything, but the longitude is trivial, so it's also always 1. So this should be sum of W alpha 1. And this should be, so here the meridian is alpha, sorry, I do the arrows in the wrong direction. So the meridian is alpha, and if you check carefully, the longitude, if you trace, is also alpha, is equal to alpha. So the first computation gives 1, 1, 2, 2, 3, 3, beta is equal to alpha, and the second computation gives alpha 1. Okay. So now let's compute the invariant for any knot. Okay? So, so first of all, here is a little program to compute invariants. So let me explain how it works. So suppose you have a knot. Suppose you have a knot, and then it's a class that I teach, it's always the same knot, right? And it's labeled 1, 2, 3, 4, 5, 1, 2, 3, 4, sorry, 5 and 6. So how does the computation go? First of all, I cut it completely. So I cut here and wait. I cut before each label. So I cut here and here and here and here and here and here. And now, so I put a cut ahead of each label. So now I have to, so now I have 3 crossings, each of which is labeled 2 labels. It used to be 4, but I separated 1 label away. So this crossing is labeled 1 and 4. This crossing is labeled 2 and 5. And this crossing is labeled 6 and 3. Okay? So I put an R matrix, an R element, or I multiply 3 R elements, as I should, because there are 3 crossings, and I multiply them, and each one lives in 2 tensor factors. So overall, this lives in the product of 6 tensor factors. And the R elements are R41, this is for this crossing, R25, and R63. So now I have something living in the 6th tensor power of my algebra. And all I have to do is to re-glue. So multiply 1 by 2, and then multiply 2 by 3, and then multiply 3 by 4. But what this really means is that I multiply 1 and 2 putting the result in 1. And then I multiply 1 and 3, multiply 1 and 3, putting the result in 1. All the way to multiply 1 and 6, putting the result in 1. And when I'm done with that, I have the value of the invariant in tensor factor 1. So that's exactly what the program does. So first of all, it sees a crossing. If it's a positive crossing, you know, the program positive asks if a crossing is positive or negative, and you can figure it out from the orientation of the lines, but it's pre-written, so it's a waste of your time, so I'm not showing you. But you know, if you really, really wanted, you could do question mark positive Q, and the computer will tell you the definition of, double question mark, and the computer will tell you the definition of positive Q. So it involves lots of private names because it's not supposed to interact with visible names. So, but it's really a very, very, very short program. Anyway, so what I do is I take the PD notation of the note. Every time I see a crossing, if it's a positive crossing, I put an R matrix from L to I. If it's a negative crossing, I put an R bar from J to I. That's what come out of this procedure, if you check. And then I call Z the output of that. And then for K, running from 1 to twice the length, to twice the number of crossings, so here there were 3 crossings, so I had to go to 6. I do Z is equal to, I apply to, so K times I do, I multiply 1 and K into 1. And it just occurred to me that that's a mistake. I should start from K equals to 2, not from K equals 1. So that should be 2 here. But it's a minor, it didn't do anything bad. So here's the program. And now let's compute the table of all invariants for nodes with up to 3 crossings, up to 5 crossings. And for each one also echo how long it takes to compute. Okay? So here you go. So node 3.1 took 0.4 seconds. How long should the node with 4 crossings, how long should it take?
Twice of that.
Well, so think that you now have 2 more tensor factors, and each one is 36 dimensional. So you're kind of lucky that it didn't get multiplied by 1296. And the reason is that the reason it didn't get multiplied by 1296 is because R is relatively sparse. I mean, R lives in a 1296 dimensional space, but it's only a sum of 36 elements. So this is roughly 36 times that. And now a 5 crossing node should take 36 times as much. 36 times 14 seconds is, I don't have a time for wait for that. So let's interrupt it. Even interrupting it takes a little bit of time. Okay, a grand failure. I mean, so we got 2 nodes, and we know that as frame nodes they're different, but good, it's basically a grand failure. But you see, this is the usual well, first thing you do is you play, and it's well, then you try to optimize. Okay? Oy, we only have 10 minutes. I hope I have time to explain. But the idea with Z2, so Z2 computes the same thing, but it does it by adding crossing after crossing. So instead of, you know, if you have 10 crossings, you look at the 20th tensor factor of a space, and then you're dead. What you do is you add one crossing, multiply, add one crossing, multiply. And then, if you can, multiply what you can. And then with luck, the number of tensor factors you have to consider will never grow too much. Okay? So I don't think I have the time to go over it, so I'll just do it very, very briefly. So there is a done variable, and the done variable indicates which tensor factors. So the tensor factors, suppose the node is with 10 crossings, the tensor factors will still be labeled from 1 to 20. But many of them will be missing, right? They don't have to be continuously labeled from 1 to 10 to 20. In fact, tensor factors don't even need to be labeled by numbers. So done will be which are the tensor factors that are already participating in the computation. And then you do crossing by crossing. So you do as C stands for a crossing, as it runs through the list of crossings. For each crossing, first of all, you multiply by the correct R matrix, R element. And then, and this is the tricky thing, this is the thing that takes thinking, so I will not go through it, but the point is, if one of the indices of your crossing belongs to the done list, or rather if the done list is adjacent to one of the indices of your crossings, then you multiply. Okay, so this is a bit tricky to figure out exactly what's happening here, but the point is, you know, you add the first crossing. When you add the second crossing, if its index 2 is adjacent to an index 1, which is already in the list, in the done list, then you multiply 1 and 2, and then you save tensor factors. So let's execute this, and let's do the same, but now for all nodes with up to 6 crossings. And well, that was a significant improvement, right? The 4.1 got much better. 5 crossing nodes were unreachable before, now they're reachable. But still, one of the nodes took 5 seconds, and I think we're done, by the way. But one of the nodes took 5 seconds, and that's not very promising if I want to get to 48 crossing nodes eventually. Okay? So let's do the next step of optimization. So the next step is the same as in the Jones polynomial. So I don't want to just put in the crossings in a stupid order. I want to put the node in thin position so that the front is always as short as possible. So that's what thin position does. And in fact, this is exactly the same thin position as in the case of the Jones polynomial. So I define the command thin position, and then Z3 is simply Z2 of thin position of K. So it's really almost nothing except for, well, it's the same trick, right? So now let's do it, but now with all nodes with up to 7 crossings, and things are much better. In fact, things are so good that we begin to think that maybe we're doing well. Okay? But if you look at it more carefully, you see that actually it's a stupid invariant. There are only 2 or 3 values. It's a very, very, very weak invariant. And this can be quantified. I mean, I can explain why it's a weak invariant for the group S3. And in fact, it's part of homework assignment 3. So if you look carefully at homework, if you understand homework assignment 3, you'll realize that it also implies that it's a very, very weak invariant. But this is just the group S3. The group S3 is almost a billion. So, you know, usually in group theories, things start being interesting with S5, or with A5 more precisely, with the the first simple group, non-abelian simple group. So let's go up. We want to go to S5, so let's go up to S4 at least. So let me declare the group S4 and print the multiplication table just for fun. Here's the multiplication table. And then let's do the same as before, but for S4. Okay. Bad news. So you see, the factor now with each time is not 36 squared. So it's not, each additional crossing does not potentially add 6 to the, multiplies the complexity by 6 to the 4th, but by 24 to the 4th, which is absolutely awful. So let's kill this computation. Even killing it will take time. Mathematica doesn't like to kill very long expressions at once. Like it collects all the garbage, it takes time. Okay. Okay. The next clever thing to do is to say, well, you see, all the meridians in a knot are conjugate. Right? This meridian is a conjugate of that meridian that are conjugate by the arc, essentially by the longitude, by the piece of the longitude that it connects. So I can fix a conjugacy class and then restrict my attention to alpha and beta running over that conjugacy class. And you can check that WG restricted to a fixed conjugacy class. So you can check that this works, this makes sense. You can check that multiplication makes sense. And that's all we need to compute invariance. Well, we completely give up of the dream of doubling strands, which is necessary to compute genus and necessary for slice knots, but at least we will be able to compute. Because these formulas, this formula, like if alpha and beta are in the same conjugacy class, you can't make this stay in the same conjugacy class. So, I mean, this fails, but at least we can compute. So again, let's declare the group S4. Let's write a little program that finds conjugacy classes. Gee, I only have 30 seconds. That's not enough time. Actually, can I go like 5 minutes over time? One no is enough. Is it okay? So, how do I find conjugacy classes? I set a C. The C is all the elements of the group. And then, so long as the C is non-empty, I take the first element of the C and conjugate it by alpha, where alpha runs over everything, and take the list of all elements that are thus obtained. That's a conjugacy class. So that's a new conjugacy class. I append this conjugacy class to the list of conjugacy classes. I remove this conjugacy class from the C, and I repeat. So this will give me the list of all conjugacy classes as the element CCS, conjugacy classes, and then I output that element. So that's what conjugacy classes does. So let's compute and set CC to be the list of conjugacy classes. And for S4, there are 1, 2, 3, 4, 5 conjugacy classes, and they're relatively short. And then I redefine, so I say, let's $CIS stand for a conjugation invariant set. In principle, just a conjugacy class. And then I redefine R to be the sum over alpha and beta over a single conjugacy class, or conjugacy invariant set. Likewise for R bar. So I redefine R by going to just one conjugacy class, and then I check Ridermaster 2 works. Ridermaster, I do a table of checks. One check of Ridermaster 2 for where CIS runs over all conjugacy classes. There were 5 conjugacy classes, so I get the value true 5 times. Likewise, I do for Ridermaster 3, and it should work, hopefully. Is it going to work? Yes. And then I define invariant number 4. Invariant number 4 is defined exactly the same way as invariant number, not invariant, Computation Program number 4 is exactly the same as program number 2. The only difference is that instead of running it once and for all, I run it several times. I do it as a sum over all conjugacy classes. So it should output exactly the same thing. But it should be much faster, because instead of 24 to the n, you get 1 to the n plus, you get the lengths of the conjugacy classes. So 1 to the n plus 6 to the n plus whatever that is, 8 to the n plus 3 to the n plus 6 to the n. That's a lot less than 24 to the n in principle. So this should be much, much, much faster. And then Z5 is Z4 on the thin position of K. So Z5 is what I care about. So let's compute Z5 for all nodes with up to 7 crossings. Woo! Oh, I forgot to actually execute this. So now let's compute Z5. Well, it's working. It's actually getting us in interesting invariants. But first of all, it's actually not working fast enough. These are still just 7 crossing nodes, and we're still talking about, 2 seconds. That's just not fast enough if you want to go to 48 crossings. And secondly, it's actually, if you look carefully, it's not interesting enough either. So you go to S5, and you declare the group S5. Here are the conjugacy classes. But now some of the conjugacy classes are actually rather long. So we didn't do so. We can start computing, but I'm running out of time, and so does the computer. So what's the conclusion of today? We have a very elegant theory, which we implemented very, very cleanly, and then we were able to implement it really, really improve it really, really dramatically. Yet overall, it's a great failure. But you see, we're still in class number 11, I think, out of 36, so we have a chance to do better. Okay, but by the way, if you don't implement, you don't know that what you're doing is abstract nonsense. That was abstract nonsense, that this is not something that's practically usable. If you don't implement, you can be delusional. Okay, so see you on Wednesday.